Let's make a start. Only three of you here, but anyway. So what we're going to do today, and probably is only going to be the only session of this week, is just to go through some exam practice questions. So these are some things you can look and work on when you're preparing for the exam, which is on May the 8th. So let's go through this sheet. So there's a collection of about 17 questions. Some of the notations are a bit different from the lecture notes. That's primarily because these are my own questions, nothing to do with the lecture notes, but it should be easy to understand what's going on. So let's go through these sequentially. So we look at question 1. So question 1 says you've got two events E and F. You can forget about this. This is some notation which is not important. And we're asked to show the following two things. The probability of E complement intersection F is equal to the probability of F minus E and F. And the probability that E and F is at least the probability of E plus the probability of F minus 1. Okay, so the first one, okay, so this one is pretty straightforward. So we know that F, the set F, can be expressed as the intersection of E with F or the intersection with F with E complement. Okay, that's one of the kind of rules that we used for these sets a while back. So what does that mean? Well, we know that this set and this set is disjoint, so the probability of F is equal to the probability of this one plus the probability of this one. Okay, and then basically it's rearranging, right? We want this one, so I just take this to the other side, and so the probability of E complement and F is just equal to the difference between this one and this one. Okay, which is what we wanted to show. Okay, the second one, so it should look familiar. This is from your midterm. So the probability of E and F is the probability of E plus the probability of F minus 1, at least that value. Okay, so we know that the probability of E and F is the probability of E plus the probability of F minus the probability of E or F, right? So this is one of the first equations we saw when looking at probabilities. Okay, we saw it the other way around. Okay, now what we know is that this number at the bottom, this number here is at least 1, okay, so, sorry, is at most 1, okay, so if I make this number as big as possible, I only make this thing smaller, okay, so this thing is at least as big as this one and this one, it's still there, and basically this one is upper bounded by 1, okay, and that's basically it. Okay, so that's a pretty straightforward one, but you wouldn't expect to get many marks for something like that in the exam. Question 2 is the Monty Hall game show. So we saw this one in lecture notes, and I think this is a nice solution to doing it. So it's the classic question. So you have a TV game show. Basically, you've got a contest. You've got 3 doors, a prize is behind one of the doors, and the idea is the contestant goes to a door, stands behind them, and says, "I think the prize is here." Then the game show host, he or she goes and opens one of the door and there's nothing behind it. And then he or she asks the contestant, do you want to stick or switch? Okay, so the question is, should we prefer to stick or switch? Well, stick means we retain the same door as we had before, and switch means we take the one that we didn't before. Okay, so when the game show host opens the door that you haven't, one of the doors you haven't picked, there's nothing behind it. So there are many ways of doing it, and this is one way, okay? So in this kind of exam context is a little bit ambiguous, but if you can produce a sensible solution, then most likely you will get all the marks. Okay, so this is so one way to solve this. So you introduce three events A, B, and C. A is the event that the prize is behind the door that you've chosen. B is the event that is behind the open door, and C is the event that is behind the remaining door. And we denote this event H sub B, which is the event that the host opens door B, okay? Which of course it does. Now what we want to do is we want to compute the probability that the prize is behind the door that you've selected, i.e. door A, given that the host has opened door B, which is the option of staying where you are, against the probability that the prize is behind door C, also given that the host has chosen door B. Okay. Now, before anything happens, the prize is equally likely to be behind door A, B, or C. So this is basically an assumption, which is that essentially it doesn't matter before anything happens that the prize is behind one of the 3 doors. Okay. Now, basically, if you read the question, what this says is the probability that the host chooses door B, given that the prize is really behind door A, right? So what that means is the prize is really behind the door A, and so both door B and C are empty. There's nothing behind them, right? So it doesn't matter to the host if he or she shows you door B or door C. So that's why you get a half for this one. In this one, well, basically this is the probability that the host shows you opens door B, given the prize is really behind door B. Well, obviously the host is not going to do this, otherwise you won the prize from the beginning. So this has 0 chance. And the last one is the probability that the host chooses door B, given the prize is really behind door C. Well, you've chosen door A. The prize is really behind door C. Okay, so if he doesn't want to show you where the prize is, he's got to open door B. So that's why that probability is 1. Okay, now given all this information in these 2 highlighted slides, one can solve the problem. Because we know from Bayes' theorem that the probability that A given HB, this is just the Bayes' theorem result, the probability of HB given A over the multiplied by the probability of A over the probability of HB. Okay, so the numerator, we know what it is. This one, this is a half, this one is a third, okay, and then the denominator, we will just use the law of total probability. Okay, that's what you do in the bottom. Okay, and then this one and this one, well, we know those numbers. This one and this one, well, this is 0, so we don't care. And this one is, well, this is 1 times a third. Okay, so that's 1/3. Okay, and if you do the same calculation, except replacing this one with the quantity C here, you'll get 2/3. So in this particular solution, it's more advantageous to switch because you're 2 times as likely to have the prize behind the door B. Okay. So that's the solution to question number 2. Question number 3 is called the prisoner's dilemma. This one is quite a nice question. And it was also quite famous. And it's a little bit challenging, so you have to think a little bit. So you've got 3 prisoners, we'll call them A, B, and C. They're in solitary confinement, and they're to be sentenced to death. But each one knows with probability with probability 1 upon 3, essentially, that one of them is going to be pardoned. So the president or the prime minister, whatever the country is going to pardon one of them. Okay, and of course they don't know which one it is. Otherwise, this is a silly, strange question. So now prisoner A, this prisoner, asks the governor whether he, it happens to be a male prison, is to be pardoned or executed. And the governor won't answer the question, but he does say that B is going to be executed. Okay, the governor thinks he's not giving any useful information, as A knows at least one of B or C is to be executed. Okay, so now this prisoner A suddenly feels much happier because he thinks his chances of being pardoned have risen from 1/3 to 1/2. The governor, who, if A were actually to be pardoned, is equally likely to give C or B's name, is mystified by A's euphoria, or A's happy, if you don't know what euphoria means. So basically, who's correct? Okay, and so there's a hint. Okay, so we'll forget about this one, because it's already a long question. So basically, the idea is we let A, B, and C be the events that A, B, or C, respectively, are to be pardoned. A, B, or C then partition the sample space. We then invent, so you're really told this information, so G of A, B is the event that the governor tells A that B is to be executed, and what we want is the probability of A being pardoned, given the governor tells A that B is to be executed. Okay, that's what you want to do. All right, it's set out for you. Okay, let's have a look. So let's look at the first part. So basically, the first thing, that's the first piece of information we're given, that the probability of A, B, or C being pardoned is equally likely a priori. There's no ambiguity there. We're told that. Okay, now this is a probability. So this probability is the probability that the governor tells A that B is to be executed, given that A is to be pardoned. Okay, so if A is to be pardoned, either B or C is going to be executed. They're both going to be. So it doesn't really matter if he tells you B or C. Okay, and this information, if you're worried, basically is stated here. So, yeah, right. So this is this information here. Okay. Right, now the probability the governor tells A that B is to be executed, given that B is to be pardoned, is 0, right? Because the B is to be pardoned, we assume the governor doesn't lie. Okay, and this one, of course, is up to debate, but it's the most reasonable thing to see. And the last one, the probability that the governor tells A that B is to be executed given that C is to be pardoned, well, basically, that's equal to 1, because basically he's not lying, but he doesn't want to give any information. So basically, he doesn't want to tell A that he's going to be pardoned or executed, so he just tells him, well, B is going to be executed, and I know C is going to be executed. The governor has the information. That's the whole point. So now basically we're just going to use the Bayes theorem. So the Bayes theorem says the probability of A given G of B is the probability of G of AB given A times the probability of A over the probability of GAB, right? So the probability of A is a third, the probability of GAB given A, that's a half, okay, and then the denominator is just going to be a third times a half plus a third times 0 plus a third times 1, okay, and if you do that, that's 1 upon 3. Okay, and so the answer is, basically the answer to this question is A, the governor is correct because basically the prisoner is wrong because his odds of being, or probability of being alive essentially, have not risen from a third to a half. Okay, now part C, the next part of the question says, what should this prisoner C feel if he overhears the information, but he thought that actually is a prison guard who asked the question. Okay, and we're given again a hint that we want to consider basically the event G, that the governor tells the prison guard that B is to be executed. Okay, so this essentially is pretty much the same question. The only thing is what we're doing, so we still have this information, is we want to consider these three events, except in the case GPB. Okay, so let's think about this. So GPBA, given A, means what? That's the probability that the governor tells the prison guard that B is to be executed, given that A is to be executed. A is to be pardoned. Okay, so if A is going to be pardoned, well, you know, is equally likely to tell them, I mean, it's B or C, so it's a half. Doesn't matter. The probability that the governor tells the prison guard that B is to be executed given that B is to be pardoned is 0, because we know that can't happen, because the governor knows that B is pardoned. So you're not going to tell the guard that he's going to be executed. And the probability that the governor tells the guard that B is to be executed given that C is to be pardoned, again, is equally likely because the guard is asking the question. So the difference between this one and this one, so if you see this one as the equals, but this one is different, right? Because in this case, it's A, the prisoner is asking the question, whereas here P, the prison guard is asking the question. And that's the key difference. Okay. So basically now you just do the computation that I said. Basically you compute the posterior probability of C. So C given GPB, which is the probability of GPB given C times the probability of C over the probability of GPB, which can be inferred by these probabilities. So basically that's a half. Okay, so in this case, prisoner C should be feeling happier if indeed it was the fact that the governor was talking to the prison guard even though he wasn't. Okay. So that's question 3. Question 4 is pretty straightforward. So this is basically the description of a binomial distribution, and I have taught you very, very specifically what a binomial distribution is. So it's like this. So a surgical procedure is successful with probability theta. Okay, theta is a number in 0, 1. The surgery is carried out on 5 patients, with success or failure of each operation independent of all other operations. Okay, so this information at the beginning tells you basically the number of successes or failures, and basically this is a collection of independent and identically distributed Bernoulli trials. Immediately you know that if X describes the discrete random variable corresponding to the number of successful operations, immediately that's a binomial. It's basically, it's completely perfectly explained to you. Okay, so now we're asked to find the probability mass function of X, as I said, is binomial, and then we want to do these 3 questions. Okay, so basically this is the probability mass function of a binomial distribution. You must include this information that X, the random variable, lies in the set 0, 1 up to n. Okay, so now we're asked the chance that essentially X is equal to 5 if theta is 0.8, and we're just basically substituting theta is equal to 0.8 and X is equal to 5 and n is equal to 5, because 5 is the number of operations that occur. Okay, and if you do that, apparently it's 0.32. Part 2, exactly 4 operations. So this is x is 4, n is 5, and theta is 0.6. That's 0.25. And fewer than 2, so we want the probability that x is less than 2 when theta is 0.3, and that's just the probability x is equal to 0 plus the probability x is equal to 1. Okay? And that's it. Okay, very good. Maybe I'll just move this a little bit. So question 5. Sorry. Question 5. So an individual repeatedly tries to pass their driving test. We suppose that the probability that the test is passed is theta, and that results of successive tests are independent. Okay, independent and identically distributed validity trials. X is the discrete random variable corresponding to the number of tests taken until the individual passes. And this is, again, if you read your lecture notes, is precisely the definition of a geometric probability distribution. So the probability mass function of this random variable, we don't have to do any work, is like this. It's 1 minus theta to the x minus 1, so I fail x minus 1 times, and then I succeed, and there's only one way of doing that. And x, the random variable, lies in the set 1, 2, because it takes you at least one test to pass. So now we're asked the question, the test is passed in 3 or less tests if theta is equal to 0.25, okay, and more than 5 tests are required for a pass to be obtained if theta equal to 0.7. So basically these ones are very tedious if you use the probability mass function, so you want to compute the CDF, cumulative distribution function, and basically that's what? Well, that's the sum from little y is equal 1 to x, where x is a number in this set, of the probability mass function over y's. Okay, so this thing is just a geometric series, and you can work out very simply that this is equal to 1 minus theta to the power x. Okay, so the geometric series, finite geometric series for geometric rate of less than 1 is the first term times 1 minus the number of terms to the power of the number of 1 minus the common ratio to the number of terms divided by 1 minus the common ratio, and then basically you get this. Okay, so that's the CDF, and now basically the answer to 1 and 2 is simple, because 1, theta is 0.25, I want the probability that is passed in 3 or less tests, the probability x is less than or equal to 3, it's very explicit, and that's just basically f of 3, so I just substitute x is 3 in this formula, when theta is equal to 0.25. More than 5 tests, so we want now the probability x is bigger than 5, theta is 0.7. Obviously, this is not a very nice probability to compute, but that's equal to 1 minus the probability x is less than or equal to 0.5. That's 1 minus f of 5 when theta is equal to 0.7, and apparently that's 0.0243. Okay, and you expect these numbers. This number is quite expected actually, because theta is 0.7. Sorry, so the chance that this individual passes their driving test is quite high. So the chance that they take six or more tests is pretty low. Okay, that's question 5. Question 6. So we have a fair coin, so the word fair is important, is flipped repeatedly, and the successive flips are independent and identically distributed, independent and identical. Let x be the discrete random variable corresponding to the number of flips required to obtain 3 heads. Okay, that is the sequence of flips which concludes once the third head has been seen. Okay, and we are asked the probability mass function of x, and the answer is very simple because that's the negative binomial distribution, where we saw explicitly the construction of this. Okay, so there's nothing else to say there. Here, this is the probability mass function of a negative binomial distribution where you want to achieve n successes, and x must be at least the number of trials to achieve those n successes, and the success probability is theta. So in this case, n is 3 and theta is 0.5, and you know that theta is 0.5 because you're told the coin is fair. Okay, so you can check, and this explanation is exactly the thing that we saw from the construction of the negative binomial distribution. So it's very explicit. Okay, so that's question 6. The rest of the questions are actually fairly computational, and they're actually good practice for you to be ready. So if you can do these questions, and I suspect that you can do them very easily, then you'll be really ready for at least some part of the exam. So for which constant values of the constant c do the following functions define a valid PMF, probability mass function, for the random variable capital X, and x lies in this 1, 2 off to infinity. Okay, so it's important to know what are the values that x has. So the first one is c times 1 over 2 to the power x. and f of x is c 2 to the x over x factorial. So it's unsurprising that we're discrete. This one tells you the random variable is discrete. And in both cases, compute the probability x is bigger than 1. Okay, so part 1. So we need the sum x is 1 to infinity of f of x is equal 1. Okay, so then basically in this case, so I have the sum x is 1 to infinity of c to 1 over 2 to the power x is equal to 1. So I can take c to the other side. So c to the minus 1 is the sum x is 1 of 1 over 2 to the power x. This is an infinite geometric series. The common ratio is less than 1. So the value of this is the first term over 1 minus the common ratio. And here the common ratio is a half. So this is a half over 1 minus a half is 1. So c to the minus 1 is equal 1. So c is equal 1. Okay. In the second case, again, we have the sum over all x's. The sum x is 1 to infinity of this function must equal to 1. So you take c to the other side. So we have c to the minus 1 is the sum x is 1 to infinity of 2 to the x over x to factorial. Okay. Now this thing is almost the exponential power series, Taylor series for the exponential function e to the power 2, except you don't have the first term. So this is e to the power 2 minus 1. E to the power 2 is positive. So that means that c is 1 over e to the 2 minus 1. Okay, and it's basically these functions are non-negative functions on this support. So that's why these are probability mass functions for these values of c. Okay, now to find the probability that x is bigger than 1, that's the 1 minus the probability that x is equal to 1. So basically all we have to do in this case is you substitute x is 1, you multiply by c, and you do 1 minus that, okay, which happens to be a half. And similarly the same thing for this one. This is e to the 2 minus 3 over e to the 2 minus 1. E to the 2 is about 8, so don't worry, that's not negative. Okay, question 8. So if you remember, you should remember hopefully at some point we talked about the lack of memory property for the exponential distribution. Well, the geometric distribution also has this property. So x is geometric theta, so that means that this probability mass function looks like that. And so we want to show for n and k in the set 1 up 2 off to infinity that the probability that x is equal n plus k, given that x is bigger than k, is the probability that x is equal to k. That's what's called the lack of memory property. And if you recall, you can check in our lecture notes that we had looked at that for the exponential. Okay, so we recall the following. So basically we know that this is the CDF. That's something that we derived just a few moments ago. So though the probability that x is bigger than n is 1 minus the probability x is less than or equal to n, so that's 1 minus theta to the power n. Okay, and basically the key to this solution is knowing the CDF. Okay. Now, the probability that x, so now what we want to do is we want to work with this quantity. So the probability that x is equal to n plus k, given x is bigger than n, is the probability that x is equal to n plus k and x is bigger than n over the probability x is bigger than n. Okay, so this quantity in the denominator, we've just calculated it. This one, well, that's equal to the probability x is equal to n plus k, because if x is equal to n plus k, by construction, x is bigger than n. Okay, because remember, n and k are in the set 1, 2. So any k that I put in here in this set, immediately I'm bigger than n. Okay, now the probability that x is equal to n plus k, well, I know that. That's just from this. It's 1 minus theta to the power n plus k minus 1 times theta. Okay, so then you just substitute these two expressions in here. So that's what I just said, and that's the denominator, and you get 1 minus theta k minus 1 times theta. That's exactly the probability that x is equal to k, which is exactly what we wanted to show. Okay, that's it. It's just about understanding what is the geometric PMF, knowing how to calculate the CDF, and then substituting into the distribution substituting into the conditional probability formula. Okay, right. So question 9. Question 9 says you have got a pair of random variables x and y. They're both discrete and they lie on the set. So x is in the set 0, 1, 2 off to infinity. Y is in the set 0, 1, 2 off to infinity. And this is their joint probability mass function. Okay, so this basically means if x and y belongs to this set, i.e. x is in the set 0 to 1 off to infinity, y is in the set 0, 1 off to infinity, then this is the probability mass function for some constant c. Okay, so we want to find the c and the marginal PMFs of x and y and show that x and y are independent random variables. Okay, so we must have that the sum over all x, y's of f of xy is equal to 1. So basically we have the sum over all xy's of this function. So that means that c to the minus 1 is the sum over all of xy's. Now the nice thing about this function, this double sum looks horrible, but it just factorizes into a product of two sums. And these product of two sums are identical. This thing is the exponential power series for e to the power 2. This is equal to e to the power 2. So the constant to the minus 1 is equal to e to the 4, i.e. c is equal to e to the minus 4. Okay. It's basically the same thing as we were doing before. Okay, now if you know a lot about probability mass functions, you're done, because basically this is clearly now basically the product of two Poisson random variables with parameter 2. But if you want, you will do the question properly. If you want to find the marginal probability mass function of x, okay, f of x, I fix x in 0, 1 off to infinity, and I sum the joint probability mass function over all possible values of y's. Okay, so I take out the values of the sum which depend on x. It just comes out the sum, and then I'm summing this. Well, this is 1 by construction, so this is the probability mass function of x, and you can do, it's exactly a symmetric argument for the probability mass function of y. Okay, and then if you multiply f of x by f of y, you're going to get back f of xy. Okay, for every x and y in the support, and that's what we want to do. Okay, very good. Okay, so now the next question. So x is binomial, so this is binomial 1p1. Don't worry about these notations. We will use a standard notation from the lecture notes. It's just my own notations. So don't worry about the notations too much. So this says that x1 is binomial 1 with probability success 1, p1, and independently x2 is binomial 1, p2, and z is the random variable x1 plus x2, and we're asked to find the expected value of z and the variance of z. Okay, well, at least for those of you who come to this class, this should be straightforward for you. The expected value of z is equal to the expected value of x1 plus x2, and we know, we have seen it, that that's equal to the sum of the expected value of x1 and x2. x1 is binomial 1p1. You can compute exactly this expectation because it's p1. This is just the sum over two numbers. The expectation of this is p2, so you get p1 plus p2. Very simple. The variance, so x1 and x2, you know they're independent, so the variance of the sum is the sum of the variances. And again, you can easily compute the variance of x1. It's just equal to p1 times 1 minus p1, and this one has the variance p2 times 1 minus p2. You can compute it easily. The expectation is like that. It's just a sum over two numbers. And it's similar, you can do the same for the expected value of x squared. They're equal. That's why you get the variance is p into 1 minus p squared, because it's p. This number is p, so I get p minus p squared is the variance. Okay, question 11. Question 11, you have a continuous random variable, so at least you know from the beginning the class of random variable that you're looking at. It has support in the closed interval 0, 1, and its cumulative distribution function is given by this. Okay, so alpha and beta, they've got some constants and they've got some constraints. Okay, and c, we want to find c in terms of alpha and beta, and then calculate the expectation of x. Okay, so this is pretty straightforward. Okay, so the first thing is that we know that f of 1 must equal 1. Why is that the case? Well, because we know that the probability that x is less than or equal to its most large value must be equal to 1. Now, its most large value is 1, so we must have f of 1 is equal 1. Okay, so if I substitute x is 1 into this formula, I get alpha minus beta, so we must have c times alpha minus beta is equal 1, so c is equal 1 over alpha minus beta, and don't forget here that alpha is bigger than beta, so alpha minus beta is positive. Okay, so we now have this constant c. Now we want to find the expected value of x. Okay, so there are a few ways to do this. The easiest one is to find the PDF and then just compute the expectation from the formula. Now, what is the PDF? If you know the CDF for a continuous random variable, then you know the PDF if the function f of x is differentiable in x, which it is in this case. So all I need to do is I differentiate this function with respect to x. That gives me my PDF. Okay, so I fix x in x. This set x is this. Okay, I differentiate this function with respect to x. It's pretty straightforward, because basically the c is 1 over beta, alpha minus beta, and if I differentiate the alpha beta x to the beta minus 1 minus alpha beta x to the alpha minus 1. So this is the PDF when x is in this set x. Okay, now all I need to do is to compute the expectation. So basically the expectation is equal to the integral over the space 0 to 1. This is my coefficient alpha beta, this is out here, and here I got x to the beta minus alpha because I multiplied through by x. Okay, and now this is a straightforward integral. This is integrand of this is x to the beta plus 1 over beta plus 1. This is x to the alpha plus 1 over alpha plus 1. And when x is 0, we don't care. So we're basically going to do alpha beta over alpha minus beta multiplied by 1 over beta plus 1 minus 1 over alpha plus 1. And if you do some algebra, this is the answer. Okay, and the reassuring answer is less than 1. Well, you can show it's less than 1, which is what you would want. Okay, question 12. So question 12 says you've got a pair of random variables x and y. They're continuous. Basically, x and y. So x is positive. This is what this thing means here. X is positive, and x and y is real valued. And this is their joint CDF, a cumulative distribution function, which looks like that. Okay, so we're asked to find the joint PDF, and we want to know whether x and y are independent. Well, this is again is a very straightforward question. The reason why it's straightforward is I look at this, and I look like this looks like a CDF, and this looks like a CDF. In fact, I know this one is a CDF because that's the CDF of an exponential random variable of parameter 1. This actually turns out to be a CDF as well. It's a CDF of something called a Cauchy distribution, which you have seen is a special case of the T. Anyway, if you don't know that information, this is how you proceed. Okay, so first of all, define the joint PDF. We maybe have not seen this in lectures, but it doesn't matter, you'll know this now. That if you want to find the joint PDF for two random variables given its CDF, I just differentiate that function twice, first with respect to x and then with respect to y. The order won't matter in this course. Okay, so if I differentiate with respect to x, well, obviously this function does not depend on x, and this one is going to give you e to the minus x. Okay. Now, if I differentiate this function now with respect to y, well, this one is of 0, and the derivative of tan to the minus 1, you can check it, is 1 over 1 plus y squared. You can do that by implicit differentiation methods. Okay, and I know for sure that they teach that at A level. Okay, so that's the joint PDF. Okay. Now, what we want to do, so that's the joint PDF for x and y in this support. Now we want to know whether x and y are independent. Okay, so again, it's pretty obvious to me because I can see that this is a product of two functions, so they pretty much are. But to verify that, we know that we can show it very simply. Well, the integral between 0 and 1 e to the minus x dx is 1. The integral between minus infinity and to infinity of 1 over this thing, this one again integrates to 1. You know the integral, by the way, because you have this indefinite, the derivative. This is the derivative of this. Okay, so basically fx of x is this, fy of y is this, and f of xy is the product. So x and y are independent. Okay, it's fairly should be fairly straightforward. Okay, so question 13 is now getting slightly more difficult. So we're given a pair of random variables x and y. They're continuous and they belong both to 0, 1, and this is the joint PDF. Okay, we want to find the constant c, yet again, and then we want to know if x and y are independent, and then finally we want to compute the probability of this set. Okay, so for the first part, well, they look pretty independent to me. Again, it's a product of functions of x and y. But that's not the answer to the question. So first of all, the integral over 0, 1 squared of this function must be 1. Okay, so that is that c to the minus 1 is equal to this double integral. And this double integral, well, if you integrate first with respect to x, the integral of x is x squared over 2 between 0 and 1 gives me a half. Okay, and then I integrate y, which is y minus y squared over 2 between 0 and 1, which in the end gives me 1 over 4. So c is 4. Okay, right. Okay, now what we want to do is we're going to work out whether x and y are independent. So let's find the marginals. So the marginal f of x is in the set 0 to 1, is the integral between 0 and 1 of the joint PDF 1 minus y dy. So if you do that, that's y minus y squared over 2 between 0 and 1, which gives you a half, so I get 2x. That's the marginal on x. The marginal on y, well, it's the same thing. Okay, I just integrate this function for c equal to 4 between 0 and 1 with respect to x, where y is in the set 0, 1. So you get like this. Okay, so if I multiply these two things together, I basically get that's equal to the joint PDF. So x and y are independent. Okay, now the next part is a little bit more complicated. So I want to find the probability of this set. Okay, this one is a little bit more complicated. So, Okay, so where we're going to do y then x. So remember, you want to do the integral. So let's have a look at the region. Let me see that I can see it so that before I write it. So this is the region of integration. So I know that if you're sitting far away, you can't see this, or if you're watching a video, you can't see this. But anyway, I'll just have to draw it out and hope for the best. So this is the x-axis. On the x-axis is the y-axis. This is the point 1. This is the point 1. So this box is... This box here, this square, is the support of the random variables inside the box. And we want to find the probability of this set that x is less than y is less than 1. Okay, so this is the line. This is the line y equals x. Okay, and now I want x to be less than y. So this is the shaded region. So I'm integrating over this region. Okay. That's what I want to do. So now I just want to compute the double integral of this function when c is 4 over the shaded region. Okay, so in this particular question, I'm going to go y then x. So if I want to integrate with respect to y, you draw a line parallel to the y-axis. You find the point at which you first enter the region. That's when y is equal to x, and I leave when y is equal to 1. So I get the integral between x and 1. Okay, and then I move my line over the support, so x is going between 0 and 1. Okay, and that's why I get my 0 to 1. And once I have this information, then basically we're basically done, because the integration is not a difficult task. Okay, so here I do y first, so I get y minus y squared over 2. I go between x and 1, so if I substitute x and 1 into this, I'm going to get this thing and multiply by 4x. So I get this one. Okay, and then basically I just integrate this function. So this one x squared, this one is equal to 4 over 3x to the power 3. This is, why is it minus? There's a big, well, there's a mistake. One of these is a mistake. I'm not sure which one. I'll have to check it. I'll check which one. There's a mistake. I mean, obviously, if I differentiate this one, I'll get 2x to the power 3. So that might be one of these is wrong. Anyway, the answer should be a sixth. Okay, so question 14. So 14 is again one of these more tricky questions. So here you have a pair of continuous random variables x and y, and we're given that the joint probability density function looks like this, but here's the support of these random variables. So here we know x and y are positive, but the sum of x and y is less than 1, and we want to find the marginal PDF of x. So the main trick in this question is really understanding what this set is. Okay, once you have that, then it's not a problem. Okay, so let me just try and write down what does this set look like on a graph. I'll use blue this time. So the set, what it looks like. So first of all, this information, x, y, and r plus, means obviously you're in the positive quadrant of the x, y axis. But you're also the x plus y is less than 1. Okay, so if I draw the line, this is the line y equals x minus 1. Oh, no, it isn't. 1 minus x. Yeah, that makes it a bit better. 1 minus x. I've forgotten these things. Okay, so this point is 1. This point is 1. And this shaded region, that's where we define our probability density function. So this is the support on this triangle. Now, in order to find so basically x and y, so we know x is at most 1 and y is at most 1. Okay, so now if I want to find the marginal PDF on x, what I want to do is I want to integrate with respect to y. So I want to integrate this way. Okay, so what I know, no I don't. What do I want to integrate with respect to y? I want to go the other way. I'm making mistakes this morning, afternoon even. So I want to integrate with respect to y. So y goes between the region 0 to 1 minus x. Okay, so that's where this integration limit comes from. Okay, and x must be between 0 and 1. That's how you get the support of x. Okay, and now we're off to the races again. It's pretty much just doing the integral. Okay, so now I want to compute this integral, 24xy, integrating with respect to y. So that's 24x, y squared over 2 between 0 and 1 minus x, which gives me 24x, 1 minus x squared over 2, which is obviously 12. X, 1 minus x squared, where x is in the set 0, 1. And I just explained to you where that information comes from. Okay, so we're almost finished, so I'm going to keep on going until we get there. This one is a nice, I like this question because it's basically a nice result which comes from, well, it's a nice result which is used in many areas. So here what you're told is we have a random variable which is non-negative and it's continuous. And as this is the support, so R plus, there's a mixing up, but this is actually what it means. This one, you can forget about it. So then it has a PDF little f and a CDF capital of X. Okay, so now we write the expectation in its integral form on the left-hand side, and changing the order of integration show that this is the case. Okay, so it's not so obvious why is the case. It's actually a very nice result. Okay, let me show you how to do this. So the expectation of X, by definition, is the integral between 0 to infinity, because we have this information, x times f of x dx. Okay. Now the trick in this is to basically rewrite x as an integral. So x is equal to the integral between 0 and x dy. Okay, so what I'm trying to say, if I can highlight it properly, is that basically this integral is x. Okay, I integrate 1. The integral of 1 with respect to y is y. Y goes between 0 and x. That's x minus 0 is x. Now the trick is to reverse the order of integration. Okay, so this is the integration range. I'm integrating this function f of x and 1 with respect to y then x, and I want to integrate 1 then y. So again, this is another trick where really we need to understand the integration region that we are working on. Okay, so let's try and do that. So again, we have the y and x axis. Okay, I have the line y is equal x. This is the line y equals x. Okay, and basically what we're saying is y goes between 0 and x goes between 0 and infinity. So this is the region that we're integrating, this infinite range. Now what I was doing in the integral that I'm highlighting is I'm integrating y then x. Now what I'm going to do is I'm going to do x then y. Okay, now if I do that, I draw a line parallel to the x-axis and I draw a line and an arrow. Okay, so the first time in which this x enters this enter this region is when x is equal to y, and it never leaves it. So x goes between y and infinity, and y goes between 0 and infinity. Okay, and so then basically this is what I have left over. All I've done is change the order of integration. Now the key point is that this quantity here, this one, is 1 minus f of y. Okay, so I get this integral, the integral between 0 to infinity, 1 minus f of y dy. Okay, and it doesn't matter if I integrate with respect to y or x, so I can write that as 1 minus the integral, 1 minus f of x dx. And that's exactly what we want to show. And you can check that if x is real valued, that this proof fails. So it's only true for, I guess, x in 0 infinity or minus infinity 0 or something, right? You can't be on the real line. Okay, but it's an alternative way of computing expectations for non-negative random variables. It's a result that I'm pretty sure that we didn't derive in the lecture course. Okay, so 2 questions left, and that's basically all there's left in the course. The following, it's quite a nice question. The annual profit in millions of US dollars of a manufacturing company is a function of its demand. X is continuous and corresponding, if X is a continuous random variable corresponding to demand in a given year, then the annual profit is like this. Okay, now X is supposed to be exponential 6. We want to find the annual expected profit. Okay, so the easiest way I think to do, so I want to compute the expectation of y, which is the expectation of 2 times 1 minus e to the minus 2x, where x is exponential 6. So basically we're almost done. Because this thing, I integrate between 0 to infinity, x is exponential 6, so that's where I get my support from. 1 minus e to the minus 2x, that's the same, 2 comes out, and the PDF of exponential 6 random variable, it looks like this. And now I'm just doing integration. Okay, so I take the factor 6 outside, so 6 times 2 is 12. I get e to the minus 6 minus e to the minus 8. That's minus 1. If I integrate that, that's minus 1 over 6 e to the minus 6x. Minus plus, because I get 2 minuses here, 1 over 8 e to the minus 8x. between 0 to infinity. Obviously, when I'm in infinity, I don't care because I'm going to get 0 out of these. And so if you substitute basically x equals 0 and multiply by minus 12, you'll get a half. So the expected profit is 500,000 US dollars. Okay. Okay, very good. So the last question, again, these are just, it's not covering all the possible things we can do. It's just the questions I had available for us to do. So here we're doing the following. So we're given two PDFs, F1 and F2, and they have some support x. And we let g of x equal pi times f1 of x plus 1 minus pi f2 of x, where pi is in the set 0, 1 is known. And we want to show that g of x is a PDF on x, and that the expectation of x with respect to g, which is like this, is pi times f, the expectation with respect to f1 plus 1 minus pi times the expectation of x with respect to f2. Okay, we have the definition here. Okay, it's pretty straightforward. First of all, basically pi is positive, 1 minus pi is positive, f1 and f2 are positive. So of course this is a non-negative function, right? This is a non-negative. So basically g is non-negative, so that's good because it's a candidate for being a PDF. Now we want to show that it integrates to 1. Okay, so the integral over all x's of g of x dx is the integral over all x's of pi f1 of x plus 1 minus pi f2 of x with respect to x. So we know that expectation is a linear operator, so basically we can sum these two integrals, and I can take out the constants. That's what we've done here. Now this one's a PDF, so that's 1, that's a PDF, that's 1, so I get pi plus 1 minus pi is equal 1. So the function is indeed a probability density function. It's actually quite well known, this is something called a mixture distribution, where probability pi we're from this population with probability 1 minus pi and with this population. Okay, part 2. So the working lifetimes of two batteries, this is the last time I have to talk about working time of life batteries, are regular or long life. Okay, so regular Z1, that's gamma, so this is a gamma distribution, the parameter is 4, 2.5, this is a gamma distribution with 11 and 4. Okay, and in an exam we will tell you the information that this has an expectation, this random variable has an expectation A over B. Okay, but in the year that I taught this in particular course, the students could already do that, so that's why I'm telling you that. So a battery is selected at random from a mixed box which 80% contains 80% regular and 20% long life, and its lifetime x is measured. Find the expected lifetime. Okay, so of course what we're doing is that basically the density function of this random variable x, which has 80% regular and 20% long time, is this is 0.8, this is the PDF of a gamma 4, 2.5, and this is 0.2, and this is a gamma PDF of 11, 4. So to find the expectation, we just use this formula. Okay, so basically the key point is that the expectation of this, as I told you, you would be told that this, in this particular year for this course, the expectation of this is 4 over 2.5, the expectation of this is 11 over 4, so the expectation of g is just equal to 0.8 times 4 over 2.5 plus 0.2 times 11 over 4. Okay, this is, oh sorry, I forgot to tell you, I haven't solved this question yet, sorry, I'll solve this afterwards. Okay, that's the solution. So we want to derive this formula. I don't think we did that. Or did we do that? We just did that, right? No, I didn't do that. We want to show that the expectation is like that. Sorry, it's been a long week. So I want to, so this is the last part. No, sorry, I've done it out of order. So I want to show that this is the case. Okay? So the expectation with respect to g of x by definition is x g of x. G of x is equal to pi 1 minus pi plus pi f of 1 plus 1 minus pi f2. Okay? So now we can take, this is a linear operator, so I can split up these two integral, the sum of the integral is the integral of the sum is the sum of the integrals, and I take out x and 1 minus pi. So here this is x f1, this is x f2. By definition this is pi, this one is e f1 of x, this is e f2 of x, and this is the formula that what you wanted to derive. So sorry I forgot to say that. Okay, and so those are the 17 questions. I thought it would take me a bit longer than it did, but, well, it didn't. So that's basically all the information. Yes? Oh, sorry, you just put your arm back. Sorry. Okay, so that's all the information that I have for you. In fact, that's much more than all the other two classes. They don't have this information, so I expect this class to do a little better than the rest of them because I've prepared you a bit more for the examination. That's all that I have for you. I'm going to stop the video lectures from today. And if you have questions for your examination, so just to let you know, so you know the exam is on May the 8th, which is a Wednesday, 5 o'clock, multi-purpose sports hall 5, I recall. If you have questions for your exam, there are two ways to do it. One is to send me an email, and as long as it's something about the notes or the things that I've taught, they should be fairly easy for me to respond. Or you can set a meeting, which might be better because you trap me into the situation where I have to answer your questions. The other piece of information which is important is the week after next, which is the week starting the 15th of April, I will not be here because essentially I don't have any teaching, and the problems class is on the national public holiday. Okay, so between the 15th to the 19th of April, I will not be available for face-to-face meetings. However, I'll still be meeting, so you can send me an email. I'll still be working, so you can send me an email. Okay, so just if you want to revise, these are the times we'll be available. Of course, I will put this information on Alumnus. And the other thing to say is that the midterms have been graded, and I have to figure out how I can put that information on Alumnus in such a way that you can access the information without seeing everybody else's. I may ask, I could actually, it's easier, the easiest thing for me is to actually put the Excel file on Alumnus, but I've been told that I shouldn't do that because it has all your names and matric numbers, which apparently is privileged information. So it might take me some time to work out how to do that, but hopefully in an hour or so it'll be up. I'll try to do that. I mean, if you're very desperate, you can come with me to my office. I can show you your score right now. Okay, so that's all. Thanks very much for your attention and for the course. And if you have questions, you can email me. Okay, thank you.